In this video, we will look at another extremely popular application, www. This stands for World Wide Web. This application provides a tremendous wealth of information, so much so that we are addicted to it. One day of no internet access, we all suffer from withdrawal symptoms. In fact, many people don't even distinguish between the web and the internet. Web is actually an application that runs on the internet. Web has its origins in CERN. Where have you heard this name before? Right, this is the world's largest particle physics laboratory. Tim Berners-Lee in 1989 came up with a proposal to distribute this high energy physics data, that is reports, photos, blueprints, among the collaborators. And that proposal finally led to the World Wide Web. In 1993, the first graphical browser, Mosaic, was released. I cannot even imagine how they managed without a graphical browser. Web became so popular that in 1994, W3C, that stands for World Wide Web Consortium, was formed to develop the web and the standards that support web. There's a lot of jargon associated with web. I think most of this jargon you're already familiar with, but let me still go over it. So when you access this information, you basically access it in the form of web pages, and these web pages consist of a base HTML file which includes several referenced objects. So these objects could be other HTML files, JPEG images, Java applets, so on. And within these web pages, there's often text or image that links to another page. These are called hyperlinks. They are often highlighted by some means. Each object that you want to retrieve is addressable by a URL that stands for Uniform Resource Locator. For example, for this GIF image, this is the URL associated with it, and this URL has a specific structure. The first portion refers to the protocol, which is the HTTP protocol. This refers where the image is hosted, that is the host name, and this specifies the path within this particular host where the image is located. So these web pages are written in hypertext markup language, HTML. You must have already hosted your own web pages on the web, and you probably know more about this than even I do. So HTML basically describes how a document is to be displayed. There are other assisting tools such as cascading style sheets, XML, XSL, so on. I'm not going to get into any of these details since it's really not quite networking. So these web pages are viewed by a program called a browser. You're all familiar with many browsers: Internet Explorer, Google Chrome, Mozilla Firefox. The actual protocol employed by the web application is the HTTP protocol. This stands for Hypertext Transfer Protocol. Like I had mentioned before, this is based on the client-server model. The client, basically the browser, requests web objects and the server is going to respond with a status code and the requested object if it is present on the server. So you do want reliability of your transfer. So HTTP operates over TCP and the servers listen on port 80. There are two versions of HTTP. This is the older version, HTTP 1.0, defined in this RFC. The later version is 1.1. This is what is extensively used. One important thing you should note about HTTP is that it is a stateless protocol. The server maintains absolutely no information about the user across requests. A server just looks at what was requested and just returns it. It does not keep track of what the earlier requests were, when they were requested, who sent them, so on. There are two types of HTTP connections. One is called non-persistent, other is called persistent. Let's first look at non-persistent. So this non-persistent connection is used by the older version of HTTP, that is 1.0. So when using non-persistent connections, at most one object is sent over a TCP connection. In other words, if you want to retrieve 5 objects, you need to open 5 TCP connections, even if the 5 objects are on the same server. So what do you think is the problem with this approach? Well, it is rather inefficient in terms of the operating system overhead, especially a server is going to serve many clients and each client will request a HTML page which in turn will have many objects embedded within it. It will then have to handle so many TCP connections and each TCP connection involves state maintenance. So this will lead to a lot more overhead at the server. So this can also increase response time. What do I mean by response time? Basically the time when a request was made and the object fully received. For a given object, what do you think its response time will be when using TCP? Express this as a function of round trip time. So whenever a request is made, before you even can convey it, you need to establish a TCP connection. Remember, TCP has a three-way handshake. So you will send the SYN flag. In response to this, you will get the SYN plus ACK. And in response to this, you have to send the ACK. But as I mentioned, you can always piggyback data on top of it. So request can potentially be sent as part of this third. So this is one round trip time. And in response to this, the other end, which is the server, is going to respond. This is the reply. And if it's a very large file, this will take some transmission time. But if it's a small packet, it will come right away. So this will be 2 round trip times plus whatever time it takes to download that particular object, which is the transmission time of the object. Let's work out a small example. Suppose you are using HTTP non-persistent connections and you want to download a HTML page which in turn has 5 embedded objects within it. Now what will be the overall response time to display the web page fully? By fully I mean including displaying these 5 embedded objects. Now assume that an object fits within one packet and assume also that the object requests are made sequentially. In other words, you request for object 1, only when the reply for this comes you request for object 2, so on. So calculate what the overall response time is going to be. Since I had mentioned earlier that for a given object you are going to take 2 times round trip time, the transmission time is negligible in this particular case since the object fits within one packet. There is the base HTML web page, so that is what you will download first. That is going to take 2 round trip times. And then for each of these 5 embedded objects, you are again going to establish 5 TCP connections to retrieve them, and each of that is going to take 2 round trip time. So this will take a total of 12 round trip times. So this calculation was based on the requests being sequential. What if the object requests are made parallelly? In other words, you first request the HTML web page, then you examine the web page and notice these 5 embedded objects, and you ask for these 5 embedded objects parallelly at the same time. So what do you think your overall response time in this case is going to be? So here for the base HTML web page, it is going to be 2 times RTT, and these 5 embedded objects, since they are going to happen parallelly, they're all going to take 2 RTT still. So your overall response time will be 4 RTT. As mentioned, the problem with non-persistent connections is the server has to manage too many TCP connections, which can be considerable overhead. So this was rectified in HTTP 1.1, where the server connection is left open for subsequent requests. Basically, if we are still dealing with that particular page with 5 embedded objects, so you're going to establish the TCP connection, send the request, you're going to get the response, and you could use the same TCP connection to send these other object requests as well. So within this persistent connection also there are 2 modes of operations. One is non-pipeline, where the new request is only sent after the previous request completes. In other words, you open the TCP connection, you send the first request. Once this request finishes within the same TCP connection, you are going to send the second request. And once this finishes, you are then going to send the third request. Now, if you are using HTTP persistent connections and you want to download this HTML page which has 5 embedded objects, how many round trip times will it take? Assume the same assumptions as before. Basically, the base HTML page is going to take 2 round trip time, and each of these 5 embed object is going to take 1 round trip time. So this will lead to 7 round trip time. So this is 7 RTT compared to the 12 RTT from before, because we have eliminated 1 round trip time resulting from each TCP connection. You could also have a pipeline mode where multiple requests can be sent at once. Again, going with this example, you first establish the TCP handshaking, then you send the request, which is the base HTML. Now you examine this web page and then notice there are 5 embedded objects and you could send them right away. So these are all the requests that are going one after the other. You're not really waiting for an answer to come before sending this. Now in this particular case, what is your total response time going to be? Well, it's a bit tricky because it's a function of in what state the TCP is in. Is it at slow start or is it in equilibrium where its window is sufficiently large? So why don't you tell me what is the minimum response time that it can take? Well, it can be as low as 3 round trip time, assuming that this is the 2 RTT corresponding to the base HTML. And if you can manage to send all of these, because these requests are very small, you can potentially send all of them in the same TCP segment. And then from the other end, you may also get all the responses from it within the same TCP segment. Or even if they don't fit within one single TCP segment, if your window size is sufficiently large, you can potentially send them all back to back and you'll get responses accordingly. So we'll take a break here. We will look at the HTTP message format as well as look at a demo of HTTP in a later video.